Well, I need to begin my talk with an apology. I mean, I could many potential apologies once for this outrageous title, but that's not the apology that I want to make. So I misread the web announcement of the program a little bit. So I thought I had more time for this talk than I actually have. So I figured out this just in the coffee break. So actually I had a coffee break to figure out what to do, and I needed to adjust a little bit. So what you will see me doing during this talk is flipping forward through slides, and I apologize for that sincerely. So I adjusted, and what I'm going to do with this talk is the following. I will give you an introduction to the subject of measurement-based quantum computation, and then present my claims. I think I will not have the time to explain much about them, but if you are interested in them, then please consider this an invitation to talk to me, and then we can discuss it in more detail. I know there are people here in the audience that are familiar with this area of work, so some of the comments I make will be addressed to them, but the bulk of my talk will hopefully be addressed to a more general audience. So, my student Boya and I are here to get a conversation going that was described in the previous talk. Namely, we have a physicist and a logician talking to each other. But now there is a third person, which is us. We are physicists by training, but with measurement-based quantum computation, we have moved into a topic that is probably computer science, foundations of quantum mechanics. And being physicists by training, we know what question marks the physicists will throw at us, and even more so with this subject, talking about measurement-based quantum computation as a point model of space-time. But we don't really know what the logicians are going to ask us. And we are here to understand those questions, and we hope to receive them. Okay. So let me begin by explaining what measurement-based quantum computation is. It is a scheme of universal quantum computation that is based on measurement. You know that there are two different kinds of evolving states in quantum mechanics. It's unitary evolution, measurement. Unitary is deterministic and reversible. Measurement is probabilistic and not reversible. It turns out you can build quantum computation on either. If you use unitary evolution, you end up with a so-called circuit model, it's a standard model. If you use measurements, then you end up with this. And what is it? So you begin with a suitable entangled state of many, many qubits that we call a resource state, and why will become clear on the next slide. And then you perform a quantum computation by measuring each qubit by itself. So if you perform a measurement, you can choose the observable that you measure, but you cannot choose the outcome. So there is randomness in this scheme, and you have to deal with it. You have to prevent this randomness from creeping into the logical process. The question is, can it be done? Well, and the answer is yes, otherwise I wouldn't be standing here. But the message to take home from this slide is that information is written into this initial state and processed and read out from it by one qubit measurements only. So the one qubit measurements really drive the process of computation. And to get you a better idea of what that resource state is for, is maybe discuss the scheme in terms of entanglement. So we are burning entanglement of the initial resource state to get a computation result. So all the operations driving the computations are local ones, and therefore entanglement can only increase. So the resource state is a very important part of the computation. If you use the wrong resource state, you will have no computational power. If you use the right initial state, then you have the power of universal quantum computation. And most quantum states will be wrong. So there's only very special choices that you can make here to get universal quantum computation. So you can study this subject for various purposes. I mean, for physical realization, but that's not something that we want to discuss here today. You can study it from the viewpoint of computational models. details, and this is our main motivation, and you can discuss it for a topic like the emergence of temporal order. And that is a very exploratory topic, but that's what I wanted to go into today. Okay, so yeah, now I'm getting into this area of measurement-based quantum computation as a toy model for general relativity, and that is of course outrageous. So let me, well, but maybe justifiable, and that's why I'm talking about it here. So the problem of unifying the theory of gravity with the theory of quantum mechanics has a very long history. And it's an unsolved problem to this day. Quantum mechanics describes the world of the small, and gravity describes physics on the large scale. But the two of them don't fit together very well. What has been accomplished shortly after the completion of quantum mechanics itself was the unification of quantum theory with a special theory of relativity that happened in a paper by Radboud in 1928, but there essentially it stopped. And since then, I suppose, suggestions for how to merge the two theories, general relativity and quantum mechanics, are invited. Yeah, and so here we are. The question that we pick, and which we think is a question that such a unified theory must be able to answer, is there a quantum mechanical origin of time? And well, in our toy model of measurement-based quantum computation, we have such a link. I mean, we are not claiming at all that we can make a significant contribution to unifying quantum mechanics and GR, but I think maybe we have an interesting idea that is worth further exploration. So this is the main question that I want to address. Is there a quantum mechanical origin of time? But then, suppose you have that, there are four. I mean, if you want to propose measurement-based computation as a toy model for GR, I mean, you must show more than just this. And here's a list of questions that we believe a physicist would throw at us. So the one question is there a notion of neighborhood between space-time points in measurement-based quantum computation? We live in the four-dimensional manifold, so yeah. Another question is there a counterpart to Lorentz transformations or conformal transformations in measurement-based quantum computation? So we think we have a candidate for that. Is there a metric that we don't know yet? So I think it's a question that we will be asked, and we have no answer to that yet, but I have listed it anyway. And then one may ask which phenomenology of general relativity can be modeled in measurement-based quantum computation. And we know that light cones can be modeled, we know that closed time-like curves can be modeled, just to make you aware of that. Closed time-like curves are permitted by the Einstein equations. And yeah, measurement-based quantum computation analogues of those have been shown in previous works. And what we would like to add to that is the notion of event horizons. Okay. So now let me introduce the main link that we have here between measurement-based quantum computation and temporal order. So what's the link between those two concepts within the realm of measurement-based quantum computation? So what you find is in measurement-based computation. Also, maybe I should first describe this picture here. What we see is a resource quantum state that would be good enough just to implement the one qubit unitary. So we have qubits here in a row. We want to do just what I said. We know that we have randomness in the measurement outcomes, and we want to prevent this randomness from creeping into the logical processing. So what has to be done, it turns out, is that we need to adjust measurement bases according to measurement outcomes that have been obtained on other qubits. So the measurement basis to be chosen here will be a function of those measurement outcomes. But this has an implication for temporal order. It means that these qubits here must be measured before this qubit Otherwise, there will be no way of adjusting the basis. So, we therefore find that the randomness of quantum measurement leads to a temporal order among the measurements. So this is, if as a simple scheme, if we, for this model of measurement-based quantum computation, so the randomness of quantum mechanical measurement is the reason for temporal order, and if we combine it with the principle that this randomness should not enter the processing, then we get temporal order out of this. Of course, this principle talks about information processing, and so this cannot be generalized straightforwardly to a wider setting, but maybe there is a more general principle that is applicable to a wider setting. But this is the line of reasoning, how we get from the randomness of measurement to temporal order within the framework of measurement-based quantum computation. So that was my intended outline. I wanted to start with an introduction to measurement-based quantum computation, and I'm in the middle of it, and then review some previous work on temporal order in measurement-based quantum computation, then review our results, and then come to the outrageous part. So I need to shorten this up a little bit, and now you start to see me skipping. And I think I skipped the definition of the resource state. Let me just talk a little bit more about the measured observables. So what you see here is how this business of adaptation of measurement basis works. So in fact, it turns out that the picture is very simple. There is only, for every qubit, there's only two possible measurement bases, so you can label them by a binary integer. And yeah, so the question now is then how this number, this binary number, depends on the measurement outcomes. And that will also be very simple. It's just a parity of certain measurement outcomes. And also the measured observables have a very simple form. And in this line is actually a little bit more simpler than generally allowed, but it should be enough for the moment. So you're choosing an equatorial plane in the Bloch sphere. Okay, so I mean every measurement of one qubit can be described by a ray on the Bloch sphere, but we are not considering all rays. Rather, introduce some x's here, x, y, and z. So rather we are considering specific planes in the Bloch sphere. It could be the xy plane, for example, and then we would have a ray lying in the xy plane, and it would be specified by a particular angle, phi, and this is what you find. This is the observable that's written down here. And you could also use the three other equatorial planes, the xy, the xz, and the yz equator. Anyway, so this is the measured observable, and okay. And here again you see how temporal order comes about. You measure a qubit here, and its measurement outcome may feed into the choice of measurement basis over here for some other qubit. And then this leads us to the notion of forward cones. So we call the forward cone of a particular qubit the set of all those other qubits whose measurements basis depend on that particular outcome. And then similarly, you can talk about the backward cone, be the reverse of that. Okay, so just note that this temporal structure is compatible with what you have in relativity. Namely, we have no absolute time. We have a binary transitive relation as our temporal relation. I mean, that sounds a bit unspecific, binary transitive relation. So think of it as a partial order, for example, in which you have, in addition, anti-symmetry and error fluxivity. But that would be a little too restrictive because it would exclude closed time-like curves, which is something we want to model here. So I'm running short in time, right? So how much time have I left?
Oh, 10 minutes.
10 minutes, thank you very much. Okay, so let me just briefly go through known results in this area of measurement-based quantum computation and temporal order. So the question is, does the temporal order somehow emerge? Is it already specified from other pieces in this construction? And now I realize that I skipped a little bit too quickly. So what is a graph state? A graph state is a particular type of resource quantum state that we could think about. So it is a so-called stabilizer state. That means it is the joint eigenstate of a bunch of Pauli operators, of commuting Pauli operators. And this is what they look like. And so here you see the graph coming up. Here's what the stabilizer operators look like. In this picture you have a qubit associated with every vertex of a graph, and then the stabilizer operators are like this. You put a Pauli spin flip operator on a particular vertex, and Pauli Z operators in all of its neighbors, and that's one of those stabilizer operators, and the neighborhood relation is given by that graph. Okay, and all those operators together single out a unique quantum state, and that's our graph. So that's what we're talking about. Okay, and it has been shown by Dan Brown and company that if we know the measurement planes for the measurement of all the qubits and the graph, that almost uniquely specifies the temporal order of the computation, but not quite. You need, in addition, a set of qubits that can be measured first, and you need to know a set of qubits that can be measured last. So that is, in a way, a seed of temporal order. And if you have all those three pieces taken together, then you can completely figure out what the temporal order is. So temporal order per se is not implied just from the state and the measurement planes. You need a little bit more of information. Okay? And then the question arises, so if you don't know those sets, then maybe you can go through all the possible combinations. So the question arises, which sets are admissible here? And this question has also been answered. So a necessary condition has been given. So the adjacency matrix of that graph, restricted to the proper subset of rows and columns, must have an inverse. So the question that now is open is, can all these, just given the graph and the measurement planes, can the resulting temporal orders be classified? And this is one of the questions that we are asking, that we are answering with our. Okay, then there has been work on closed time like curves and measurement-based computation. Just skip that. So let me just present to you the results of our work. Here they are. I have skipped now through a bit of my presentation. So let me just state the results, and if you're interested in them, I'd be happy to discuss that with you. So first, so I should explain to you what those processing relations are. So it turns out, so I have discussed those objects before. So this is the vector that contains all the choices of bases. This is the vector that contains all measurement outcomes. And this matrix T here is the influence matrix that contains all information about temporal order. Okay, and similarly we have a relation for the classical output of the computation that's also linear. So what we have found is that the processing relations, if properly extended, they are in one-to-one correspondence with the basis of a certain matroid that encompasses all the information about the resource state and the measurement planes. And the other result that we have is that the classical processing relations by themselves determine everything that we need to know about the resource state and the measurement planes. And let me skip right through the end of this section and explain the second result. So you could ask the question, what is necessary to define a measurement-based quantum computation? So there is four sets of objects. Well, there is the measurement bases for the local measurements, and they split into two parts. So they split into the measurement planes, i.e. whether we choose the xy equator here, the yz equator, or the xz equator. And, well, the remaining information to specify a measurement basis is this angle here, the measurement angle. Okay, so we have the measurement angles and we have the measurement planes. And then third, you need to specify the resource that you use for computation. And fourth, you need those processing relations that govern this adaptation of measurement basis business. If you think you need all four to specify quantum computation, but now it's easily to show that the measurement planes and the resource state really specify too much, because you could rotate either. You could rotate the measurement planes, you could locally rotate the quantum state in the same way, would still give you the same information. So you can compress this to an object that contains all this information up to equivalence. But then it turns out, and this is our result, that this resulting object is really specified by the classical processing relations if you require that there's no randomness in the computation, in the logical processing. So, yeah. Okay, so you end up only with those pieces, and all the other stuff is new in the computation. Good. So that's the summary of our results, and now let me just briefly go into this more adventurous part. And so we want to answer a couple of questions. Is there, for example, a counterpart to the Lorentz transformations? And finally, although I think I will not have the time to get through it, is there a counterpart to event horizons here in this model? So what we are looking at is here is an operation that we call the flipping of the measurement plane. So recall that measurement bases need to be adjusted according to measurement outcomes that have been obtained elsewhere. So the way you do that is very simple. So if the measurement outcomes of other qubits tell you so, to flip the measurement basis, you just take a reflection about this vertical axis here. And now you could ask yourself, well, why not flip about the horizontal axis instead? It turns out this is a completely equivalent method of doing this, so this would correspond to measuring this lower observable here as opposed to this one. And the two are related by a simple sign factor. So you could compensate for that sign factor. So here are two equivalent procedures for measuring at a particular qubit. You could do the vertical flip of the measurement basis if necessary. That would be equivalent to flipping horizontally, but then not outputting the measurement outcome, but rather offset it by this variable q that specifies the measurement basis. By offsetting the measurement outcome of this, you would just exactly compensate for that factor. So you may ask yourself, then is this equivalent to doing the adaptation of measurement basis this way and just outputting the measurement outcome itself? And the answer is that this is sometimes possible but not always. So it is always possible if the influence matrix, that's the matrix that governs the linear processing, has no diagonal part. And then what we obtain is an operation that resembles local complementation that may be familiar to people in graph theory. So the end of this is that we end up with a transformation that preserves temporal relations, that acts locally on the measured observables, and that generates a group And the question that we're asking is whether this justifies us to call this a measurement-based quantum computation counterpart of the Lorentz or conformal transformations. So I understand that this last part was a little bit quick, but I just wanted to give you a glimpse at what we are looking at. So let me now, so this was a proof of why it preserves the temporal relations. Let me just skip ahead to my conclusions here. So the main idea, which was the reason why I was presenting, is that here in this measurement-based model of quantum computation, we have an origin of temporal order in quantum mechanics, and the question is, can we generalize that? And I have suggested, so I have presented to you, without explaining much, two novel results that we have in the theory of temporal order of measurement-based quantum computation. And we have suggested a measurement-based quantum analog of a Lorentz transformation, and what I didn't get to is we also have an analog of event horizons. But I would be very happy to discuss all these things with you. Thank you very much for your attention.
So measurement-based quantum computing is a fairly instrumentalist concept, like operational. You got the measurement guy who picks the plane, does the corrections. So where is this sort of role of the external observer in this model, or what it plays in?
The role of the external observer?
It's like measurement-based quantum is a very controlled kind of operation. Like there are all these corrections and these things. So where in this sort of toy model, what takes the role of this sort of external person who's picking the planes of the measurement and then doing the corrections?
Yes. Okay. So so the question is, so does there need to be such a guy? And I mean, maybe to vary your question a little bit, I mean, also that guy may instead choose whatever he likes. I mean, he would not need to follow those rules. And yeah, so what takes the role of the external observer? Or I mean, or in other words, is there room for an external observer here in this model? And for the moment we would keep with the operationalist viewpoint that there's just a set of rules, and those rules could be obeyed by a circuit, yes, by an object that has no free will and may not be able to use any free will to violate those relations. So it's just implemented, sort of these rules are just implemented by a device, and yeah, we are not discussing the role that any external observer may play.
So you said usually one expects measurement-based quantum computing to be deterministic.
Yes.
Due to choices of control. Is this still holding?
Yeah. This is sort of the core of it. Yes. They are imposed, and this is really part of it, and this is very central to it. We need to impose these rules in order to make the connection between the randomness of measurement and temporal order. Without imposing these rules, there would be no link. So it is very important. Then so what? Can you please raise again your objection or comment?
No, there was no objection.
Yeah. Yes, it was. Yes, this is absolutely central. We need to impose these rules. These rules form really the link between the randomness of measurement and temporal order. Without those rules, there is no such link.
Yeah. So this is a little bit related. So if you were presenting MBQC as a computational model, you would discuss the fact that you would implement various algorithms and show computation completeness and so on. Now here you've said in some sense there is an algorithm which is more or less representing some condition, but you're fixing the resources you need for an algorithm at the beginning, and then you get your temporal order and so on. So I'm wondering what's the I mean, what's the analog of the fact that you could pick different sets of resources to different algorithms, and what does that correspond to in the space-time point of view? Is it that you generate space-time with different interesting features depending on which algorithmic resources you start with?
Yes. All right. So let me. Okay. So I hope I'm. Okay. So let me answer this in the following way. There's two parts here: algorithms you want to implement, resource states that you're using. So we are confining our attention to stabilizer states. And I mean, if you had a specific algorithm, you could do this on a specific stabilizer state. Any specific algorithm, any specific stabilizer state. If you have an algorithm to start with, also from knowing that algorithm in some other description, say the circuit model or whatever, you could work out the temporal order. Okay, but then sort of the question would become kind of lame and uninteresting. So we are assuming that we cannot work out the temporal order from some other description. So we don't know what algorithm is supposed to be implemented. We are just given the resource state and the measurement planes, and we're asking the question, from that information alone, can we recover the temporal order?
Okay, if it is super quick.
Well, it's hard to see. Well, maybe, it seems to me that the temporal order is a prerequisite rather than the result of measurement computation. I mean, you have to make a rule which says use the outcome in the past. You cannot make a rule use the outcome in the future.
That is true. That is true. But we are, if you do not, if you haven't given, so let me go back to that slide of that ground. Okay. So suppose you don't have that temporal order given. Just from the symmetries of that state, can you recover it? That's the question. And the answer to that question is, well, not completely, but we can go a very, very long way. The temporal, just from looking at the state and that information over here, temporal order is very, very constrained. The possible temporal order is very, very constrained. And this is related to symmetries that those states possess.
Okay, so let's time to speak again. Yeah, so the program says that this session is until 20 past, but mistake is it? Or yeah, let's say that we continue until half past 12. Randomness. Wait. Pointer. Robot. No, don't.